I'm really excited to talk to you tonight about finding oceans on moons within our solar system. This work was done by me and a lot of the colleagues at the Jet Propulsion Laboratory. And so the outline, what I'll be talking to you tonight about is, I'll give you a quick biography, a little bit, expand upon about a little bit more of what Nick said, and then provide an introduction and motivation for ocean detection and actually characterization. I'm going to talk a little bit about this concept of what's called magnetic induction. And this is the mechanism in which we use to find these magnetic fields. And even though the physics behind it might be a little complicated, hope the visuals that will be shown will help you better understand what we're doing. And then I'll be talking about the magnetic environments of the outer planets, and I'll get into why it's just the outer planets, not any of the inner planets. But then also go into ocean detection and characterization, how we can do this on a single flyby, and how we can characterize on a multi-path mission. And then I'm going to go into the Europa Clipper mission, which is what I spend most of my time on these days. Okay, so really quick, just to add on to what Nick said, I'm from Yardley, Pennsylvania, just outside Philadelphia, which means I'm missing the Eagles game tonight, but I will watch that a little bit later. Not a big deal. I went to Penn State University, and like Nick mentioned, I went to school, actually, I got accepted into the professional golf management program. I really liked golf, and I thought I was going to be a professional golfer one day, and maybe could have, but I had a really interest in science and technology. But also, you know, my family is from an athletic background. Both my parents were gym teachers in high school, and my brothers actually played. My brother played for the Philadelphia Eagles. He was a backup kicker for David Akers. My younger brother played for the USL, played for Marshall University right here. But I was very interested in math and science and building circuits when I got to college. So I told my guidance counselor, I'm going to drop out of this major. He thought I was crazy, but it was a good decision for me. I ended up in a good spot. Went into astrophysics. Guidance counselor told me it's very hard to find a job in astrophysics, so I thought the next best thing would be go into engineering. So I went to electrical engineering. Here is the first robot I've ever built up here. And this is the first sun sensor I built, which was flown on a spacecraft at Penn State. So this led to some really good opportunities. One of them was an opportunity to work at NASA Ames Research Center in Mountain View, California. And here I got to work on some really cool things. You know, using my electrical engineering degree, I was able to use a lot of signal processing and artificial intelligence. And here we were able to design an 8-legged scorpion robot, which used an artificial neural network to stabilize imaging systems. So that was a really cool project, and as Nick said, that really sold me on working for NASA. Then I went back to Penn State after the internship and completed my bachelor's in electrical engineering in 2004 and my master's in EE in 2007. And then I spent 2 years at Boeing, actually. Got a little tired of school. Went to Boeing for 2 years, worked on basically spy satellites for the government, so I can't talk much about that. But it was fun work, but there was no science. So I actually went back to school to get my PhD. Here's my advisor, Patrick Lenahan, with Beaver Stadium there in the background. And I got a PhD in engineering, science, and mechanics. And then I was accepted into NASA's postdoctoral program in 2013, where I now work today. Really quickly, an overview for those who are not familiar with the Jet Propulsion Laboratory. JPL is one of 10 NASA centers around the US. What makes JPL different from the other NASA centers is that we're a federally funded research and development center, an FFRDC, which means we're actually run by Caltech. So I'm actually a Caltech employee, not a civil servant. But anyway, JPL is located in Pasadena, at the base of the San Gabriel Mountains, not too far from the beach. And so JPL is basically NASA's lead for robotic exploration of the solar system. And one of our biggest goals, as Nick mentioned, is to find life elsewhere. And what is the best place to find life? And the answer to that question is simple: find where the water is. But you might ask, where is the best place to find water? Or what instruments can you use to find water? And if you can't see an ocean, so an imager won't work, how do you find the water? And the answer to that question is using a magnetometer. And a magnetometer basically measures magnetic fields, and hopefully I can explain that to you. Okay, so what's the motivation for finding ocean worlds? We call them ocean worlds. So these two missions back in the day, Cassini, which actually performed its grand finale of Saturn back in 2017, it found the first evidence of water in the plumes of Enceladus. These plumes were ejected from the actually southern hemisphere of Enceladus, and when the magnetometer flew through, it determined that the ion cyclotron waves associated with those plumes contained ionized water. And then the Galileo mission, this is a mission to Jupiter back in the late 90s, essentially detected a induced magnetic field signature with the magnetometer that pointed to a global subsurface ocean. And this is the process in which I'll be talking about today, this magnetic induction phenomenon. So we have some other missions in the queue that I'll talk about. Europa Clipper, Juno, actually just made a few passes of Europa and Ganymede. That data hasn't been published yet, or at least for Europa, because that pass was about a couple weeks ago. And then Dragonfly, we're going to be flying this is actually a mission led by Johns Hopkins University, the Applied Physics Laboratory, to study chemicals in Titan's atmosphere and on the surface to help provide more clues about subsurface ocean that moon may contain. And the decadal survey is out, and this basically means that NASA is going to be prioritizing missions to Uranus and even possibly Neptune. Okay, so when we go to pick a mission and determine what moon to fly by to look for these oceans, we have to have some motivation for going there. And what we like to look for is evidence that there could be an ocean. So one of these features is we look for diverse geological surface features that are consistent with an ocean. For example, ice-covered surfaces, also smooth craterless surfaces caused by regeneration from beneath, as oceans can sometimes regenerate material and remove the scars of meteor impacts. And this can be in the form of cryovolcanic convection and tectonic movement. And then also, like I mentioned, active plumes, like we see in Enceladus, which is a moon of Saturn, Triton, a moon of Neptune, and then Europa, which is a moon of Jupiter. And then the second process is that you need some kind of heating mechanism to maintain a liquid water ocean. And these tidal heating can arise from either tidal heating, which is the non-circular orbit of a moon around its planet. This causes periodic contraction of the planet, and this causes internal friction processes to maintain a heat source such that the water can be liquid. And then also radiogenic heating. This is the decay of radioactive isotopes with long half-lives, and this also can sustain a liquid water ocean. So the most compelling evidence that we have to date that oceans actually exist in our solar system comes from the magnetometer. Here are passes of the Galileo passes of Callisto and Europa. They're labeled C3 and CE4 passes. And many of you might not be familiar with magnetometry, but basically you can think of it as a vector with an amplitude and orientation. And this represents the X component, the Y component, the Z component, and the magnitude. And what you'll notice in both of these traces is this little blip in the middle of the signal, or in the spectrum here. And this blip is associated with what we call an induced magnetic field, or just a dipolar field. And it turned out that a magnetic induction response from a subsurface ocean was first proposed by Margie Kivelson and others to explain the data that on these passes. And that they were able to show that this magnetic signature is actually synchronized to Jupiter's rotation, which means that this signal, when you fly by at another time, changes phase or shape, in other words. And this led us to believe that there's not a permanent field inside these planets, but something that is changing as a function of time. And the best way to explain that is a global scale subsurface ocean beneath the ice layer. Okay, so what are the other possible ocean worlds in our solar system besides Earth? We know Earth has an ocean, obviously. We can see it. But these other moons, for example, Europa, Callisto, and Ganymede, we know that the surfaces are water ice. And we also have great data from Europa and Callisto in the magnetic field measurements to indicate that there is a subsurface ocean. The next body, Io, which is the inner moon of Jupiter, actually does have an ocean too. It's very volcanic in nature, actually, and it's got a magma ocean, and because it's conductive, we can actually sense its effect as well. We have the moons of Saturn. We think Titan has a magnetic field that we don't know about its magnetic signature. We haven't passed close enough yet. But Enceladus, we do have data to show that it has a subsurface ocean. And obviously, you can see its outer shell is completely water ice. So that's definitely a good indication that it's got a subsurface ocean. And then Mimas is the other contender. Its outer shell is rocky ice. But because of its location within Saturn, we could use magnetic induction to investigate whether or not it has an ocean. And I like to throw up this little highlight here too. This is looks very much like the Star Wars Death Star, so it gets a lot of praise for that. And then the Uranus system, there's 5 major moons. So both Neptune and Uranus were only visited by one spacecraft, and that was Voyager back in the 1980s, Voyager 2. And it didn't fly close enough to any of these moons to determine whether or not it had an ocean. So right now we're currently in the planning to plan some of these missions to both of these systems. And Triton is the other one that I'll talk about later in my presentation. Okay, so real quick, I'm going to talk about magnetic induction, a little bit of physics for you. I'm going to keep it at a very low level in hopes that you understand it. But it starts with Faraday's law of magnetic induction. And sorry for the math, but it's really simple. All this means, this equation here means is you have a time-varying magnetic field, a changing magnetic field that varies as a function of time. So basically, just think of a bar magnet moving it back and forth. This creates an electric field, okay? And this electric field can drive current in a particular system if it's in a conductive medium. So take, for example, a simple coil right here and a stationary bar magnet. There's going to be no current induced in that coil. But as soon as you start moving this bar magnet, you induce you create an electrical current around the coil, and this induces a magnetic moment that tries to cancel the magnetic field that's perturbing the system. So what happens in the planetary system is you have the same thing. You have Jupiter's magnetic field, you have a rotating body. This changes the magnetic field in the vicinity of Europa and all the other moons, creates an induced response if the salty subsurface ocean is conductive. This will create a secondary magnetic field that you can sense with a magnetometer. So what causes the variation in the magnetic field? These field lines actually should look kind of familiar to you. If you've ever seen the field lines associated with a bar magnet, this is what we call a dipole magnetic source. And the planetary magnetic fields look very similar to this, as illustrated here. One thing to notice is, though, we call this the magnetic axis, this magenta line, and it's tilted with respect to Jupiter's spin axis. So when these things rotate, essentially you have this magnetic field lines that wobble up and down, and this causes the time variation at the magnetic field at the bodies of interest. Similar with Uranus, we have a significantly larger tilt. And then Neptune, we see a tilt of about 47 degrees. And it's this characteristic that allows us to perform the magnetic induction experiment at the moons. Saturn is its own case. Its magnetic axis is perfectly aligned with its spin axis, which means that as Saturn rotates, the bodies will always see the same magnetic field. However, a lot of the moons have eccentric orbits, which means they move closer and further apart as they orbit. And therefore, they see variation in fields that way. So we can still perform magnetic induction at these moons. Here's another thing of what I just said. Here's the magnetic field dependence of a dipole. Just the simple equation here. And basically, if you have a moon, if this is your planet and you're looking down on the orbital plane, you have a planet that orbits in a perfectly circular pattern like this. Essentially, you have no change in magnetic field. But as soon as your orbit becomes elliptical like this, you have different positions of the bodies with respect to each other. So this changes this R right here, which changes your B, your magnetic field. Similarly, if you have an inclined orbit like here. So now we're looking at the z direction and the up direction, and your planet we're looking now at the orbital plane. If you have an inclined orbit, essentially your magnetic latitude, this theta up here changes, that will change B as well. So just because the bodies change position with respect to each other, you can see this changing magnetic field. And here's just some of the moons in the solar system in which we can use this technique in. I'm not going to talk too much about this, but basically there's two different periodicities that we can use to probe these bodies. One is the synodic period, the rotation of the planetary body, and the other is the orbital period. And so there is a dependence on how far that wave can penetrate. So if you have a long magnetic wave, essentially it can penetrate deeper within your conductor. And in some cases, some of these moons have really strong ionospheres. And an ionosphere is basically a plasma in which you have conductive ions flowing, and that actually prevents magnetic fields from penetrating. But if you have a longer wavelength, like an orbital period, that takes a really long time to generate, that can actually penetrate the ionosphere and perform magnetic induction within the ocean. Okay, so now I'm going to get into some nice visuals. I'm sorry if that was over your head, but here's some nice visuals that hopefully will help explain the situation a lot better. So here we're looking at Europa orbiting Jupiter, and again our spin axis is defined by the white. Our magnetic axis is the magenta line, and as this thing rotates, you can see this is the magnetic field vector emanating from Europa, this line here, and you can see this rocking back and forth. And if we were to look at it from overhead, you can see the same thing right here. Here's Europa over here. And you can see this green line precessing about this point. And if we decompose that over here and look at the components in the reference frame of the moon, all we have is a series of sinusoids. And this is very good because we have predictable behavior that we can use this as a driving force for magnetic induction. But what you'll notice is that if you let this thing play for a little bit, this is not a perfect sinusoid of one frequency. It's composed of many frequencies from different amplitudes. So what we can do is we take a long period of time measurements at the position of the moon, and what we can do is we can do a frequency decomposition of it, or perform a Fourier transform. And that allows us to look in the frequency domain. This is plotted in period, and it shows you the magnetic field amplitude in period. So here, this strong peak right here represents the 11.2-hour synodic period of Jupiter, so the rotation rate of Jupiter. This is the orbital period. This is how long it takes for Europa to orbit Jupiter. And you see all these other beats and harmonics, and these are the beats and harmonics of the two fundamental frequencies. So we can use all this information and to look at the magnetic response from this time variation. This is important. This is where it all comes together. This is what the dipoles look like. Basically a rotating bar magnet. The 11 hours associated with the green lines represents the 11-hour synodic period of Jupiter. So this rotates as Jupiter rotates. And the blue one is a lot slower, the cyan. And this is associated with the 85-hour orbital period. And off to the right, we have the summation effect. So Jupiter's magnetic field is coming from Jupiter and coming from north to south through the body. So that's the dominant field lines you see there. And it's primarily, the greenish yellow color. But the perturbation that the ocean creates is the blue and red traces here. So it's this signal plus Jupiter's field. This is essentially what we measure with the magnetometer. Moving on to the Uranus system. This system is really exciting because the decadal survey was just released, and NASA has prioritized missions to the Uranus system. So we're spending a lot of effort designing missions to go to the system so that we could potentially characterize these major moons. The moons we focus on are Miranda, Ariel, Umbriel, Titania, and Oberon. And all these moons could potentially harbor oceans. They're further out, so they'll be a lot colder. But that just means we need a more sensitive magnetometer if we get closer. So if you're familiar with Uranus, you know it's kind of a wacky orientation. It was knocked on its side, so we're actually looking at it, as it is if we were looking at it from Earth. So its spin axis is actually pointed horizontally, and it rotates like this, but its magnetic axis is tilted 59 degrees with respect to that spin axis, so it's a really complicated system. But again, this is the same thing. We have Miranda in this inner orbit, Ariel in the second orbit, and Umbriel in the third orbit. And you'll see this precession, this magnetic field evaluated from Uranus as a function of time plotted for each one of the bodies here. And again, it's just a series of sinusoids, which is perfect for this magnetic induction experiment. Here's another view. Also, here's the Fourier transform of the signals that I just showed on the previous page. And then here are the other two moons, Titania and Oberon. And I'll talk about why they're complicated in the next slide. But one of the things I really wanted to point out, and I don't know how well it's coming through here, but if you look at this simulation over here, what you'll see is this, I've specified the magnetic axis defines where this thing points, but these magenta dots right here represent the magnetic equator. And the magnetic equator is really important because it actually carries this co-rotating plasma. And if you're familiar with E&M, anytime you have moving charge, plasma particles, this induces a magnetic field. And this actually complicates the induction signal that we're trying to measure. So we want to avoid this disk, what we call it. We call it a plasma disk. And what you can see from the simulation is that these moons, when they orbit, they're many times away from this disk. And this is very unlike the Jupiter system. Almost all the time, all the moons are immersed in this plasma disk, and it can be very complicated for inferring the properties of the ocean using magnetic induction. I spoke to you just a second ago about why we think Titania and Oberon are difficult to do magnetic induction. One is because they're further away from Uranus, so the field strengths of the driving fields are a lot smaller. But another thing is there's some seasonal effects. So here again is Uranus's rotational axis, this white line. Here's its magnetic axis. And this line right here represents the orbital plane of all the moons. And this line right here represents our magnetopause. Essentially, this is where the solar wind from the sun, so the sun is in this direction over here. Solar wind basically has a bunch of plasma that drives and defines this boundary. And effectively, it shields the magnetosphere from itself. So here's winter solstice in 2030. We can see that the boundary of the orbital plane is contained within this magnetopause. But in 2049, when we think we're going to get there, when we send these missions, our orbital planes now of Oberon and Titania get very close to this magnetopause boundary, which really complicates the effect because we really don't know how well this boundary behaves. In fact, it's very turbulent if you know much about fluid dynamics. So a lot of what we call Kelvin-Helmholtz instabilities. So we have a bunch of people looking at what's called MHD or magnetohydrodynamic modeling to help understand what these fields look like so we can interpret the magnetic field signals once we eventually get there. Okay, and now I'm going to move on to the Neptune system. So this was some work we did about 2 years ago. We proposed a discovery to the discovery concept, and where we'd fly by Triton, which is orbiting here. As you can see, it has a highly inclined orbit with respect to Neptune. And essentially, on a single pass, we planned on detecting an ocean using magnetic induction on a magnetometer. And you'll see the Triton flyby come by. Here you go. Here's the position of the spacecraft as it flies by. And essentially, Neptune's a really good system because here is the magnetic field evaluated at Triton's position along its orbit. And it's very complicated, but periodic, and that's important. We do the frequency decomposition. We can see the synodic period of Neptune. This is the 14-hour rotation period of Neptune. And then also the 141-hour orbital period. So it takes Triton 141 hours to orbit. And we can see these two frequencies in the magnetic domain and use them to our advantage. So how do we infer the interior properties of a moon based upon the magnetic field? We see the field, but how do we know what we're looking at internally. And what it is basically a bunch of forward modeling. So this is basically our model, the interior model of the moons. We have a non-conductive mantle, a conductive ocean composed of like salts, and then an ice layer that's non-conductive. And then we include an ionosphere. Triton has a very intense ionosphere. We're not really sure why, but it does. So we have to model it because it will actually also react to this time-varying magnetic field. So it induces its own magnetic field. So when we go there, we want to make sure we're not detecting the induction signal from an ionosphere. We want to make sure it's from an ocean. So what we do is we simulate both simultaneously. So I'm not going to go too much into it, but basically what you can think of it, we have this thing called the complex response function. It's a little complicated, but you can just think of every one of these single dots as a particular model. So we just modeled like 15,000 different scenarios of interior properties. So different ocean thicknesses, ocean conductivities, or different saltinesses, and then also different ionosphere height integrated conductivity, which is basically the conductivity of the ionosphere. And all the ionospheres are represented by these magenta dots. So these are the ones that gives an induction response, but there's no ocean. These are the blue ones are the ones that there's an ocean. And then the gray ones are oceans that we think are just not detectable. But anyway, we can do this forward modeling, and we forward model what is called the magnetic moment. And if you're familiar with magnetic fields, magnetic moment basically tells you the strength and orientation of that magnetic field. And we can forward model each one of these dots, these 16,000 different models in this space. And this is our magnetic moment space. It's actually a three-dimensional vector. Just two vectors are shown here, or two components shown here, my and mx. But this is not what we measure with the magnetometer. In the magnetometer, what we measure are these things, and this should look familiar from the traces that I showed from the Europa and Callisto data. But this is the forward model of our 16,000 different interior properties of Triton for BX component, the BY component, and BZ component. So this is what we measure. So how do we get from this to go to the other space where we can determine what's an ocean and what's not an ocean? And again, another thing I'm not going to talk too much about, but what we do is we use this technique called principal component analysis, where we can shove everything into some kind of a form of AI to interpret this field data. So here's what our data looks like. What we do is we shove all 16,000 models together, we stack them together, and we feed them through an eigenvalue decomposition process, which is a simple or a fancy word for saying we find the eigenvectors and eigenvalues of this huge matrix. And we use these vectors basically to project our measurement. So here's our forward models, the blue and the magenta ones, but we have a measurement that has noise on it, a single measurement, and this is only 6 minutes of data going by Triton. And then we can use these eigenvectors to project this measurement into our forward model space. And where this dot lies in this space tells us whether or not we have an ocean, if it lands in the blue, or if it lands in the magenta place, then we have a no ocean case, and it's just induction from an ionosphere. So there's a lot of measurement techniques going out there to basically assess this phenomenon. I'm not going to talk about this too much, but it's kind of cool. So we don't really know the magnetic phase of Uranus because its outer layers are gaseous. So we don't know how fast it's spinning. We have a good sense of how fast it's spinning. So we don't really know where the magnetic field is oriented when we get there on a single flyby. So we have to forward model every phase of Neptune as we go by. And as you can see here, similar to the previous page, these are all dots here. The blue ones consist of our ocean models plus ionosphere, and the magenta dots represent our own ionosphere only. And we'd like to see separation between these two model classes so we can distinguish them when we do this method. And this is what the magnetic moment space looks like. And this is the separation. We want good separation between these two model classes to give us the best margin to be able to distinguish between one or the other. And you can see that over here. We see this magnetic separation, we called it. And we want this to be as large as possible. So this is the principal component. I'm not going to go into it, but just to show you what it looks like. Using this method, we can enhance our separation. And I like to show this plot because it subconsciously biases our reviewers into thinking they're looking at an ocean. So the reviewers at NASA really like this plot. Okay, I'm going to skip this plot. This just tells you basically what oceans we can detect and which ones we can't. The simple story is that there's some oceans we can't detect, but the majority of them we can. Okay, now I'm going to get into the Europa Clipper mission. This mission has been ongoing now for since 2015 or so. It's a very exciting mission. I'm an investigation scientist for 2 of the instruments. As you can see, it's a really complex spacecraft. This is, we have imaging systems, mapping imaging spectrometer for Europa, we call MISE, Europa Thermal Imaging System, or ETHEMIS, the Surface Dust Analyzer, or SUDA, the mass spectrometer for planetary exploration, this is mass specs, the Europa Ultraviolet Spectrograph, which is Europa UVS. We also have a radar down here, we call this REASON. And then these are the 2 instruments that I'm investigating or working on. One is the plasma instrument for magnetic sounding. This is being built by Johns Hopkins University Applied Physics Laboratory. And these are basically Faraday cups. And essentially, there's 2 Faraday cups for each sensor, 1 sensor on the base of the spacecraft and 1 on the top. And the idea of the plasma sensors is to measure these plasma fields that I was talking about so that we can correct the magnetic field when we get those readings. And here's the Europa Clipper magnetometer. It's composed of 3 flux gate sensors. Here's the inboard sensor, the middle sensor, and the outboard sensor. And you can see here the flux gate core. This is designed by UCLA. Jet Propulsion Laboratory designed all the electronics and the support equipment. And if you're interested, you can simply go to YouTube and watch a live video. I just grabbed this screenshot maybe about 2 hours ago. A bunch of engineers doing nothing, but that's the way it is. Some people always have to have people watching the equipment because it's really expensive. Make sure nothing goes wrong. But you can go to YouTube, type this in, and you can watch the live feed at any time you want. And stuff's always going on. They're starting to install a lot of the equipment and a lot of the electronics for the instruments. But the point of the story is that the Europa Clipper spacecraft is really complex. It's huge, and I have another slide to show you what that looks like. But essentially, it's so complex that from being on the team of the magnetometer team, we have to worry about every little detail on the spacecraft, a magnetic component. So there's currents, electrical currents, they create magnetic fields, magnetic materials. All these things are like a nuisance to the magnetometer. We don't want to detect the spacecraft field, we want to detect the ambient field. So another thing that I've done, which I really like this work, I just put a publication out on it, but I modeled the spacecraft component as well. And this is what it looks like. This is essentially 400 individual modeled components on the spacecraft and combined. So this is what the magnetic field signature of the spacecraft looked like. So every little one of these dots is a single magnetic dipole source. And this is what the spacecraft looks like, the field looks like as a system. And this is the first time this has ever been done. So this paper's coming up pretty soon, and there's also links to these on the NASA Clipper website, so you're more than welcome to download and view for yourself. But anyway, I thought that was pretty cool. Okay, so now just to give you a size scale, many people don't know how big this thing is. So this is the NASA Space Launch System rocket, which is currently on the Cape right now, expecting to launch, I think, next week. They've been canceling it for the past couple months, but it should be a go for a launch next week. And we do have a scalar vector helium magnetometer that's sitting at the top in one of the CubeSats, so we're hoping that that's a success. The Europa Clipper mission was initially intended to use the SLS to get us there, and it would only take us about 3 years to get to the Jupiter system. Unfortunately, we have to take a SpaceX Falcon Heavy rocket, so it's not as powerful, so we have to do some gravity assist, and I'll show you those slides in a little bit. But I just thought I'd show that there for some scale reference. Here's the Statue of Liberty, 73 meters. Is equivalent to basically 6 stacked school buses, so you get a sense of scale of how big a human is compared to this. This is the SpaceX Falcon Heavy that we're going to be flying, and this is the Europa Clipper spacecraft. And if that still doesn't mean anything to you, it's basically the size of a basketball court when its solar panels are deployed. So it's a huge piece of equipment. So when we launch, though, these solar panels will be folded in, and the boom will not be deployed. It's a coilable boom, so we can retract it. So it's basically a payload about the size of this, which fits into the top capsule here. Okay, so we plan on launching next year of about 2024 in October. And here shows our solar system. At the middle, we have our sun. This is Earth right here, this cyan line, this dot right here. Here's Mars. And then here's Jupiter orbiting out here. The green dot here is our Clipper spacecraft trajectory in cruise. And the white dot here is the JUICE mission, which is an ESA-based mission, the European Space Agency. And the reason I do both of them is because we're trying to plan a coordinated approach where we can get a lot of information about heliophysics in the solar system. So what you can see here, I'll let it loop again, but what you can see here is right here where we start to bounce, the spacecraft starts to appear to bounce around Jupiter. Basically, we have orbital insertion, and right now the spacecraft is orbiting Jupiter. But what you can see here again is the Clipper trajectory. We just did a Mars gravity assist, and then we'll come back and do an Earth gravity assist too. And again, this is because the SpaceX rocket is not as powerful as the SLS, so we need to rely on the gravity assist of other planets to get there. And then you can see the JUICE trajectory also has a couple other gravity assists too to get to Jupiter. So once we get into the Jovian environment, we perform about 40 different orbits. This is this is Jupiter. This is Europa's orbit. And these blue lines represent our orbital trajectory around a fixed Jupiter rotating frame. And we perform about 40 orbits of Jupiter, but during these orbits, we're able to pass by Europa. And the reason we orbit Jupiter is because of the fact that within Jupiter, there's a really high intense radiation belt, so we want to minimize our times within this space. So instead, we just orbit Jupiter and conveniently pass Europa. And here are different orbits. Essentially, each one of these magenta lines represents an orbit around Jupiter, but our pass near Europa. So as you can see, we have really good coverage, so we're going to get a really good spatial map of what the surface looks like around Europa and good magnetic characterization as well. And then another cool thing, this is when both spacecraft, again, green represents Europa Clipper, and the white represents the JUICE mission from ESA. Now we're looking at the Jupiter magnetosphere. Here, Jupiter's in the middle. In the middle, we have Io. Here is Europa. And then we have Ganymede, the red. And then here is Callisto. And as you can see, again, we're trying to coordinate measurements so we can understand different physical phenomenon within the magnetosphere of Jupiter. But what's really cool is that there was two independent mission designers, one from Europe and one from the United States, developing these trajectories. And coincidentally, it turns out when we plotted these things together, one orbit, not this one, you can see these, again, keep an eye out for the white and the green. Eventually, these things come together and they orbit Jupiter almost within one Jupiter radii, even less than that. I think it might be on the next one. But this is it was such a shock to see this, and it's really cool because now we can do, validate measurements, calibrate each other's measurements as we orbit Jupiter. You can see it right there. Such a cool maneuver. We're not sure if we're going to be able to maintain this because the trajectories always change, but we're going to try the best we can. And I left one last visualization of this. So I do, like I said, I do a lot of visuals of the magnetosphere. And here is one of the Jupiter system of those two spacecraft orbiting together. You can see them here. It's a lot slower motion here. So here is, and to give you an idea, Jupiter rotates at about 11 hours. So this is definitely spun up. But this is the Europa Clipper and JUICE hovering right here. And you can almost take pictures of each other. We've even done the calculations to determine how many pixels in the camera one spacecraft would look, and it's only a couple pixels, unfortunately, but if we can get closer, that'd be a lot better. But anyway, this just gives you, to bring it home, what the Europa Clipper mission is about. Again, keep an eye out in the news for this. There's going to be a lot of talk on it recently. In 2024, hopefully we get a good launch. So in summary, the complicated orientation of these magnetic fields is actually a gift from nature. These magnetic environments provide ideal laboratories to provide magnetic induction experiments to investigate the interior of these moons. And subsurface ocean detection is possible at many of the moons in the solar system, including Uranus and Neptune, which have never been investigated before. And Europa Clipper, like I mentioned, will be launching in October 2024 with the goal of characterizing Europa's subsurface ocean and assessing its habitability, right? Because if we know the conductivity of the ocean, we can assess its salinity. And if we know how salty it is, we essentially can determine whether or not there's life there or not. And this will influence our future missions, whether we want to, melt ourselves down through the ice and send a submersible, or not even at all if it's too salty. So, and then also future missions to Uranus and Neptune are definitely in the plan. So stay tuned for those. So with that, I will take any questions you guys have.
Some of the rotating diagrams, especially the last one, I noticed that in like the top right corner, there was a timestamp for the date and time.
Correct, yes.
So it actually would be moving that fast?
Yeah, so that's the real time. So yeah, just sped up. Because I'm not going to sit here for 11 hours, that'd be painful.
No.
Yeah, no.
But still, it's kind of crazy to think that that all happens within the span of a day.
It does, yeah. It's pretty, I mean, think about things on a planetary scale. It's like, yeah, it's, yep.
How's it going? So, as far as I could tell, this all seemed like applicable to our solar system. So how, I guess, applicable is this method to things outside of our solar system? Yeah, I don't know. It'd be cool if you could talk about that a little bit.
Yeah, so obviously applicable to our outer solar system. Mercury doesn't have a strong magnetic field. It doesn't have any moons to probe. Also, the Venus doesn't have a magnetic field, so it doesn't have any driving fields. It doesn't have any moons. Mars does have moons. It doesn't have an extinct magnetic field, so there's no driving magnetic field to sense this magnetic induction effect. Earth is the other possibility, but we know the moon doesn't really have an ocean, but it could have conductive layers. So just as long as it has conductive layers in it, we could perform magnetic induction actually, because the Earth's got a strong magnetic field and it rotates and the moon orbits. So we definitely could see these frequencies. And we've actually sent many proposals proposing this method to look at induction on the moon. So with the new Artemis program that's coming up, hopefully somebody will be able to look into that.
I had a question, Corey. Are these salty oceans expected? So why is there so much salt?
So that's more of a question for an interior planetary scientist. So these salts are expected to be there based upon these planetary formations and the way these moons form in the first place. But yeah, without the salts, we're not going to be able to detect the oceans anyway. So
is there possibility of oceans without salt?
Yes, exactly. And that's my biggest concern is because, when we go there and we don't see an induction signal, that doesn't mean there's not an ocean. It just means it's not detectable. So, and that's definitely a possibility. But I think based upon the modeling that's been done, in fact, a lot of my group members in the Planetary and Interiors and Geophysics group, they do this. And based upon their modeling, the data suggests that there should be salt, some form of salts in all the oceans. So, yeah. Good question, though.
Hi. What would you say would be the biggest interferences with these magnetic readings?
Yeah, great question. And the simple answer to that is the plasma interaction fields. This magenta thing, these dots right here that I try to simulate plasma particles with. As you can see here, the Jovian moons, you can see them, the different colors, the cyan, red, and green. They're very close to it, so these currents essentially create magnetic fields that interfere with it, and that's a big problem for the Europa Clipper mission. We have a dedicated team of scientists who do MHD modeling to remove the effects of the plasma so we can look at the induction signal. But yeah, that scares us the most.
Okay, my question is, How come, or like, how did you end up using the SpaceX like launcher instead of the other one?
Yeah, good question. Schedule and budget. So the SLS rocket was our front runner. We only get this in 3 years as opposed to 7 years now it'll take with the SpaceX rocket. So it was definitely more advantageous for us to go with the SLS. The problem was that there were so many delays in the rocket that they weren't guaranteed to be ready in time for us. In fact, just in this last couple months, we've seen all the delays just in the launch. So that's why we could definitely be assured that we'd get to Jupiter by 2030 by using the SpaceX as opposed to SLS.
So my question is, you brought up NASA looking into missions where we drill into the oceans of these moons. What would be the logistics of something like that?
Yeah, great question. It's something that we love to think about, these crazy ideas at JPL. So drilling is one concept, but one of the things about magnetic induction that we'll be doing with Europa Clipper is not only assessing the habitability of the ocean, but also determining how thick that ice layer is. And based upon our models and current understanding, that ice layer's got to be at least 5 kilometers thick, at least. And thinking about the logistics, that's very hard to drill through. So we've come up with some really other cool ideas that allow us to use an RTG, our energy source, to melt ourselves down. So that's going to be a very long process. So we have this technology now where we have, kind of looks like a rocket, and in the front of it is an RTG, and it basically heats itself. We have these thermal engineers who design it, who allow these things to uniformly heat this body so it melts itself all the way down. And once we get below the ice shell, we also keep our mothership on top of the ice so that we can communicate with it, because talking below ice is a big problem with that. But once this thing melts through the ice, we have robots that we're building right now that we're testing in Antarctica and the Arctic, that crawls underneath the ice. We have little submersible submarines kind of things we're playing around with. So all this technology is in development right now, but you're right, the logistics of cutting yourself down through the ice is probably not going to be a realistic one.
So my question was, you have the oceans, you got water. Don't you need an atmosphere for there to be life also?
So not subsurface life. So on one slide I didn't show, you think about the thermal vents on Earth. If you've seen these discovery shows where these submarines go way down, and there's actually life at the thermal vents. So there's just, as long as there's enough energy down there, enough heat to sustain the water, there can be possibly life, and we see that at Earth. And that's another reason why we want to explore it. But thanks for that question. That's something I didn't address, but that's definitely a relevant question.
Hi there. So what I'm getting about is most of the satellites you guys have is it's a one-time mission, right?
Say it one more time. What?
With the satellites, with most missions, it's just like a one-time mission. It goes.
Yeah. Mm-hmm.
So why don't they just make it so they use the gravitation of other planets to go on different missions?
Different spacecraft to go on different missions?
No, just one spacecraft use the gravitational pull of other planets to go to multiple missions instead of just one. Would that be more time effective? So we call it delta V, which is our gas, how much propellant we have to get to a certain body, and typically the orbital mechanics doesn't allow that to happen so efficiently. We have mission designers specifically whose job is to determine how much delta V we have propellant to get to a certain body. So it's a very hard process, but I guess the easy answer is that a spacecraft can carry enough propellant to divert itself into another orbit to another planet, I guess.
Hi, I had a question. You mentioned earlier about how the craft itself emits a lot of magnetic fields and that it could interfere with the detector. Mm-hmm. How would you go about preventing that? Is it a matter of orientation or a type of material that you encase around?
Yeah, great question. So there's 2 field sources from the spacecraft that we're worried about. I showed the DC magnetic field, basically the magnetic field associated with the spacecraft as is, but then there's also currents on the spacecraft that changes the function of time, and those are the ones that are really problematic. to remove the first one, what we do, the DC magnetic field still needs to be removed, it's easier. But what we do is we have this magnetic field model, and we essentially can test it in flight. And we have 3 magnetometers on there, and what we do is we perform a technique called gradiometry. And we use, and that's why we have a magnetometer boom, to distance ourselves from the spacecraft. And if we distance ourselves from the spacecraft, we can assume that the spacecraft acts as a single magnetic source as opposed to 400 different sources. With that case, we can use the 9 measurements we get from the magnetometers to model the dipole source of the or the spacecraft and subtract it out. Now, the AC fields are a little more difficult, specifically the currents that go on the solar array. And what we do is we actually use that 7 years in flight to characterize every component on the spacecraft. So what we do is we meticulously turn on every single component on the spacecraft, every instrument, cycle through its different modes, and listen with the magnetometer, characterize its effect for 7 years. So we build up this huge model so that when a certain instrument is on, we know how to back that out of the data. So it's a very tedious process. So fortunately, we have 7 years to do it. So it was kind of nice that we went through the SpaceX rocket, actually. 7 years sounds better than 3, so.
Is the end goal or thought like trying to find habitable planets we could colonize, or is it just finding life in space?
So I missed the last part. Go ahead.
Is it just like, is the end goal like finding life in space, or planets we could colonize?
Yeah, so basically to find life. I mean, there's still potential to the question earlier that there could be life there. Down in just living in the ocean. I don't know if you've seen the movie Europa Report. Good science fiction if you guys have some time. But in that movie, there's intelligent life in the shape of like an octopus or something like that, which would be really cool. We don't expect to find that, but microbial life is definitely a possibility. So that's why we're so interested in Europa and specifically Enceladus as well.
I know you mentioned tidal forces as how the planets are being heated. What is the expected temperature of the water? I know there's subsurface, like the ice on the surface, but
Yeah.
what's the temperature of the water?
Yeah, that's a good question. I don't really know the internal temperature of the water, because it's all ice, and then 5 kilometers below there's some kind of melting, and then it transitions. That's one question I don't know, but it's near freezing probably. It's really cold. Yeah. The tidal forces and the radiogenic heating are just enough to keep it liquid, I would say. So, no tropical waters in Europa, unfortunately.
I had a question. I know you mentioned plumes of water on Enceladus.
Yeah.
I was wondering if there are any future plans in the works to maybe explore subsurface oceans there. I know you mentioned the melting through the actual ice.
Yeah.
I wondered if it might be easier there, or if there are future plans related to that.
Yeah, a lot of work going on right now. In fact, we have, a cool thing about JPL is that we have a lot of R&D going on about people exploring like really cool ideas. And, in a lot of our buildings, these mock-ups are the landers, and we have one for Enceladus, one for Europa too. And in the decadal survey, the thing that I mentioned earlier, which is a recommendation to NASA which missions to fly, one of them is called an Enceladus orbitolander. So it's basically an orbiter, but then there's a lander too. But I don't think we have plans on a specific mission to melt itself through the ice yet. I think the technology is too much in its infancy, and we need to know whether or not these oceans are habitable to make it worth going down there, because that's a really expensive task to do that. But yeah, there's definitely a lot of work going on right now for Enceladus. It's tough because there's battles, because people have their own favorites, and people want to go to land on Europa, some want to land on Enceladus, so we got a little internal battles going on sometimes. So.
Any more questions? I have one last question. I think there's another one over here. I'll ask it in the meantime.
Sure.
How accurate do you think this timetable is? Do you trust that the Clipper will be there on July 16th?
So I'm going to give you a statistic from the Juno mission. I don't know, you can look this up. I'm probably going to say it wrong, but I think the trajectory, it got to an orbital insertion back in 2017 within under a second of when it was planned.
Wow.
And it's because it's space. There's nothing there. There's no traffic. It's such a cool thing. And these mission designers, we know the gravitational effects of all the bodies so precisely, and we have really sophisticated software to plan this. It's really impressive, these guys, what they can do. So yeah, it's impressive.
Hi, this may be a bit of a hypothetical, but if it was ever thought of or planned out, what would be, I guess you could say, countermeasures if you were to encounter something unexpected like solar winds or, let's say, if the planet's magnetic fields were to somehow magically flip in the middle of this mission?
Yeah.
How would that affect
that's
your readings?
That's an absolutely great question. And that's what we worry about in the Uranus and Neptune system, because we've only visited it once. Right? And the magnetic field generation mechanism within those two planets are completely different than Jupiter and Saturn, so we know nothing about that. And we don't know the rotational phase, so there's a good possibility that the orientation of the magnetic field is completely changed. So we do worry about that, and that's why we do multi-pass missions like this to characterize as best we can. For the single pass program that we proposed to, that was a big concern of ours. Having the committee come back and say, well, you don't know that that dipole is still oriented in the same way. So that was a little scary, but yeah, definitely some concern with that.
I think we have one last question.
Yep.
Is there any added propulsion on the Clipper? Like, is there anything to do course corrections, or what kind of propulsion is it? If there is?
So yeah, what is the, we have, there's the typical propulsion. We have reaction wheels to control our attitude. And there is another propulsion mechanism, and it's not our primary one. And I honestly forget the type of technology it is, but I know about it because all the instruments have to be off when it's used. And the name is escaping me right now. I'm sorry about that, but there is a different type of propulsion that we can use to traverse through the solar system. So. No, it's not an ion. In fact, I think if you just Google it, you'll be able to find out what it is, the propulsion system. We have a really good Europa Clipper website where you can find out more about the instruments, get the live views, and learn more about the spacecraft itself. So yeah, I encourage you to do that.
Let's thank Dr. Cochrane for his great talk.
Thank you.